Okay, good day to everyone. So for now, we will discuss a very efficient and systematic way of solving a system of linear equations. So to start the discussion, suppose we have a system of linear equations as follows. So let's have the first equation as x minus 2y plus 3z equal to 1. For the second equation, we have 3x plus y minus z is equal to 0. And for the last equation, let's have 4x minus 3y plus 2z equal to 2. And our task now is to be able to solve for the values of x, y, and z. So now we will introduce the technique called Cramer's rule, which hinges on determining the determinant values of certain matrices. So for the first determinant, I will define it as capital D. And in our case, it's the determinant of a 3 by 3 matrix, which basically consists of the coefficients of the variables present in the system. So for the first column of that matrix, we will have the coefficients for the variable x. So we have 1, 3, and 4. The second column will represent the coefficients for y, so minus 2, 1, and minus 3. And the last column will represent the coefficients for z, so 3, minus 1, and 2. And then we will have also the determinant, which is called d sub x. Okay, and I'm indexing this this symbol by x because this is going to represent the determinant of a matrix where basically we are omitting the column representing the coefficients for the variable x and replacing it by the constant terms on the right sides of the equations. So for our first column, we will have 1, 0, 2. And then all the other values for the other columns will stay the same. So the second column will still be minus 2, 1, and minus 3, 3, minus 1, and 2. Similarly, we will have d sub y, which again will be a determinant of a particular matrix. But this time around, we are omitting the column for the coefficients of y and replacing it by 1, 0, 2, the column of constant terms. All the other columns are retained as before. So this is 1, 3, and 4. And the last column will be 3, minus 1, and 2. And by similar construction, we have dz, which is the determinant of the matrix where the last column is replaced by the column of constant terms, so 1, 0, 2 for the last column. And then the columns for x and y variables are retained. So 1, 3, and 4, and minus 2, 1, minus 3 for the second column. And then we will have to evaluate the values of these determinants. So the value for d is actually equal to minus 20. Now I have actually skipped the actual computation for the value of the determinants, but it will be assumed that we already know how to calculate the determinant of a 3 by 3 matrix using Laplace expansion, assuming we can determine the determinant of a 3 by 3 matrix by using at least the technique called Laplace expansion. Okay. The values of the other determinants will be as follows. So dx will be equal to minus 3, dy will be equal to 10, and then dz will be equal to 1. Now, this is where we now apply the actual technique of Cramer's rule, because Cramer's rule tells us that the value of the x variable in the system will be equal to dx over d. The value of y will be dy over d, and then the value of z will be dz over d. Let me uh, change this a little bit. So the d here is not properly written, so let me just edit that a bit. So that is supposed to be a capital D. Okay, so what we do now is we just try to substitute all the values of the determinants we have found out. And so for the value of x, this will be negative 3 over negative 20, which is equal to 3 over 20. Y will be equal to 10 over negative 20, or equal to minus half. And finally, z will be equal to 1 over minus 20. And so this will be the values of the variables that are present in the system. So x will be 3 over 20, y will be equal to minus half, and finally z will be equal to negative 20. And take note that we can actually apply this in other systems of linear equations, especially if you want to solve a system of 4 equations in 4 independent variables, or a system of 2 equations with 2 independent variables. So Cramer's rule is quite versatile and quite efficient, and it might be that it could actually be a faster way of solving a system of linear equations. So that's it for our discussion. Thank you very much.